Good morning. Here we are going to discuss some basic definitions: partitions, arcs, closed curves, simple arc, rectifiable arcs, contours, and simply multiply connected regions. Just the basic definitions. What are these? So first one is partitions. Let AB be a closed interval, and let's divide this interval into n subintervals, right? By inserting the points a equal to t naught, let's say, less than t1, then less than t2, less than t3, up to so on up to tn, right? We can divide this closed interval into the subintervals t0, t1, t1, t2, up to so on. We have like this n subinterval. So these are n subintervals. Tn point is your B and t0 is A. Then P is a partition containing these points up to Tn. This is called the partition of the closed interval AB. And the greatest of the numbers T1 minus T0, if I take the length of this subinterval, so length of this subinterval will be T1 minus T0. Length of this subinterval will be T2 minus T1. If we take the lengths of all these subintervals, then the greatest of all these lengths is called the norm of the partition, right? So the greatest of the numbers T1 minus T0, T2 minus T1, T3 minus T2, up to so on, the greatest of these numbers will be the norm of the partition, the norm of P, and it is denoted by like this, right? So the norm of the partition P is the maximum length of the subinterval. So this is the maximum length of the subintervals. Maximum length of the subintervals, right? Next is arcs. The equation z equal to zt, which is further equal to xt plus iota yt, marking this as the equation 1, where t is belonging to the closed interval AB and xt and yt, these are the continuous functions of t. So these represents the arc L in the complex plane. And if we write the parametric representation, then x is represented as xt. The value of x and y depends upon t, the point t. Normally, what is the definition of arc? It is a set of all image points of closed finite interval under the continuous mapping. So set of all those image points is the arc. Next is, what is differentiable arc L? Arc L is said to be differentiable if z dash exists. What is z? It is xt plus iota yt. If its derivative exists, then we say that the arc is differentiable, right? And also it should be continuous. So for the differentiable arc, there are two conditions. If z dash t exists, the derivative of zt exists, and also if it is continuous, right? We can also use the term continuously differentiable. Sometimes we use this term. In addition to this, regular or smooth arc. When the arc is said to be regular or smooth, if derivative of zt exists. Second condition, this derivative is non-zero. So for these two conditions, we say that the arc is regular or smooth. Then is the piecewise differentiable arc. If among its various representations this means there exists at least one representation z equal to zt, that is xt plus iota yt, such that the closed interval AB can be divided into finite number of subintervals. If we are able to divide the closed interval into the finite subintervals, on each of which z dash t exists and z dash t is non-zero. On each subinterval, derivative of z should exist, and this derivative should be non-zero on any of these subintervals. On any of these subintervals, then we say that the arc is piecewise differentiable arc. Derivative should exist and also it should be non-zero on any of these subintervals. Then is about the curves. What kind of curve is your simple but not closed? So this kind of curve is simple and not closed. This kind of curve is simple and closed. Third is closed but not simple. So this kind of curve is closed but not simple, right? For the simple curve, it should not intersect with itself. Next, there is a remark. If L is an arc, Z equal to ZT. This is the arc. Where T is belonging to the closed interval, then arc defined by Z equal to Z, where that T belongs to the interval minus B minus A. This is said to be opposite of L. This arc is said to be the opposite of the arc L and is denoted by minus L. Very important. Then is a rectifiable arc. Let an arc L be defined by Z equal to ZT, that is xt plus iota yt, where t is belonging to the closed interval AB, and let fz be the function of complex variable. This is the complex variable z, defined and continues on L. This function is defined on L and it is continuous on L. If I consider any partition P, A equal to T naught, T1, T2 up to Tn, that should be equal to B. Corresponding to this partition, L is divided into, this is the arc L. L is divided into n sub arcs, right? If this is your arc, this is the point Z naught. This means the point Z naught is depending upon the point T naught. Here the point Z1, that is depending upon the point T1. Z2 point depending upon the point T2. The value of Z2 depends upon the point T2. Up to so on, right? Here like Z is depending upon T. So we have taken all these points Z0, Z1, Z2 up to Zn, where Zk equal to Ztk, right? K is from 0 to n. What is delta Zk? This will be equal to Zk minus 1. And if I join these points by a straight line, then we are going to obtain a polygon arc, right? We have obtained this to be a polygon arc. What is the length of this polygon arc? It is the summation on Zk minus 1. We have taken the sum of all these differences where k is starting from 1 to n. We have to take the sum of all this. We say that the arc is rectifiable if the arc L is rectifiable if I take the supremum on this, the summation for the partition P, this is equal to L, and if this L is finite, we say that arc L is rectifiable. Otherwise it is non-rectifiable, right? Next is, what is the length of the arc? The length of the rectifiable arc will be, so this length is equal to, if I integrate z dash t mod from A to B, when I integrate this I get the value of the length of an arc. If we want to put the value of z dash t, then also we can write this as L equal to the integration of the square root of x dash t square plus y dash t square, the whole square, under the root dt, right? Then are the contours. A contour is a continuous chain of finite number of regular arcs. What are the regular arcs? Where the derivative of z exists and also this derivative should be non-zero. If we have the finite number of regular arcs, the continuous chain of arcs, then it forms a contour. Then what is a closed contour? If the contour is closed and does not intersect itself, it is a piecewise smooth curve. For example, this rectangular curve. It is a closed contour. It is not intersecting with itself. And the conditions, the derivative of zt should exist. It should be non-zero on any of the subintervals, right? For the smooth curve. Okay? Let's move on to the next definition. Simply connected and multiply connected region. A region in which every closed curve can be shrunk to a point without passing out of the region is simply connected. In this curve, this can be shrunk to a point without passing out of the region. So this is simply connected. Otherwise, if it cannot shrunk to a point, that will be the multiply connected. If it is having holes, right? Okay, so this is all about the definition, the basic definitions. Thank you so much. God bless. Have a very nice day.